It's an immense pleasure for me to welcome you to this special colloquium inserted in the webinar series of the Graduate Program in Physics of the Federal University of Pará in Amazonia, Brazil. I ask everyone to kindly leave the microphone and camera turned off, except for the moment you're going to speak. Questions will be allowed in the end, unless otherwise requested by the speaker. The questions can be asked using the chat, both in this virtual room and in the YouTube transmission. Today, we have the great honor to listen to Professor Gerardus at Hooft, who was awarded with the 1999 Nobel Prize in Physics, together with Martinus Veltman, for elucidating the quantum structure of electroweak interactions in physics. Professor Gerardus at Hooft grew up in The Hague, the Netherlands. He performed his undergraduate studies and obtained his PhD in 1972 under the supervision of Veltman in Utrecht University, also the Netherlands. After spending some time at CERN in Geneva in 1974, Professor Hooft returned to Utrecht, where he became assistant professor. In 1976, he was invited at Harvard in the United States of America as Maurice Loeb lecturer, and he had a visitor position at Stanford, also in the US. In 1977, he came back to the Netherlands and became a full professor at Utrecht University, which he has been associated with ever since. Apart from the Nobel Prize in Physics, Professor Hooft's research has been honored with various prizes and recognitions, including the Wolf Prize given by the Wolf Foundation in Israel in 1981, the Lawrence Medal given by the Royal Netherlands Academy of Arts and Sciences in 1986, the Spinoza Prize given by the Netherlands Organization for Scientific Research in 1995, the Franklin Medal given by the Franklin Institute located in Philadelphia, USA in 1995, Lomonosov Gold Medal given by the Russian Academy of Sciences in 2010, the Niels Bohr Institute Medal of Honor given by the Niels Bohr Institute, Denmark in 2016, and Marcel Grossman Award given this year by the International Center for Relativistic Astrophysics, the ICRA. But we are here today to listen to Professor Hooft, so that I should not make you wait longer to listen to him. Professor Gerardus at Hooft, thank you very much once again for having accepted our invitation. From this moment on, the stage is yours.
Thank you very much. It is a great pleasure for me to talk here and now in this, although I would prefer to actually be with you in the Amazon somewhere, but this will also do. The topic that I would like to talk about is fairly complicated, and I'm going to explain a number of rather unfamiliar ideas, which all have to be combined to make a theory which could be very useful for actually using
okay.
as...
I found this on the web for which could be useful. Check it out.
Sorry. It will be extremely useful for possible extensions of our theoretical understanding today about quantum gravity. In the case of quantum gravity, one will often encounter situations where you have a horizon, and the way we have to do field theory on the horizon is quite different from what people usually think. So I'll try to explain that. At the risk of becoming incomprehensible, in that case, just start shouting, this we cannot follow anymore. And I'll probably not use all my slides, but let me see how it goes. So shortly after Albert Einstein had printed his ideas about general relativity in 1915, he got a letter from a well-known astronomer, German astronomer, Karl Schwarzschild. And Schwarzschild wrote to Einstein that Einstein had written beautiful equations, but he, Karl Schwarzschild, could actually find exact solutions to these equations where Einstein hadn't been aware that such exact solutions can be written down so elegantly. And yes, he wrote them down, but Schwarzschild also was a patriot in a way. So his country, Germany, was at war with Russia, and he decided to enlist. He was at the German front line in Russia, and while artillery was shooting over his head, he had the idea that maybe this is the right moment to think a little bit about physics and to solve some equations. So he solved those equations while being shot at in the German army. But what he got out of that was the formula that you see here on the screen. I'm not going to use many formulas in this talk because I realize that maybe some people are not so familiar with it, but this is a way to write down space and time according to Einstein's equations surrounding a massive object. Here the symbol T stands for time, the R stands for a space-like distance from the origin, and omega are the angular coordinates. You don't need to know very much about gravity to understand what this equation says, but you will note that there's something peculiar going on if you approach the center of the solution by a distance 2gm. If r equals 2g times m, and g is Newton's constant, and m is the mass of the object you're looking at, but if r equals to 2gm, then this whole coefficient multiplying the dt squared vanishes. Whereas here, at the same point, you get an infinity in the expression. In other words, Schwarzschild noted that the expression becomes meaningless if r equals to 2gm. And having understood more or less what Einstein was writing, he realized that r is just a coordinate. I can add or subtract multiples of 2gm to r if I want. So let's say that r equals 2gm actually is the origin of this configuration. Then you get a point mass, and this is what the way Schwarzschild interpreted his solution. Actually, it wasn't quite correct, and lots of discussions were sparkled by this discovery, but unfortunately Schwarzschild himself wasn't able to participate in those discussions because he died soon after. At the German front, he contracted a very dangerous, lethal skin disease, and in May 1916 he deceased. And only much after that, people started to look at this solution and said there's something strange about this point where r equals 2gm. What is it? And they found that it's not the singularity at all, and that's also not where the point mass is actually sitting. It's a more subtle situation, more difficult to understand, in particular also because the sign of this expression switches if r becomes smaller than 2gm. And here it also switches. So something very strange happens with the coordinates r and t when you go to the origin closer than 2gm. And what was found then later was that r equals 2gm is a spot where you say there is a horizon. And these horizons are now a very important feature, a new feature of space and time, which did not exist in the earlier theories of particles, and now we have to deal with them. What the next step is, and I'm going to make a giant leap now from 1916 to modern times, where we are asking questions about quantum mechanics. And so what we need is a theory where quantum mechanics sets in and quantum particles are behaving, or let's say misbehaving, near the horizon, and how can we deal with that situation? That's then the important new question arising. A very important discovery, observation was made by Stephen Hawking in 1975, and that was that the object that you will be describing now, which by that time were known to be black holes, a name originally coined by John Archibald Wheeler. In this case of these black holes not only absorb things, as usually astronomers thought, these gravitational fields are so strong that all particles are being absorbed into this thing called the black hole. But Hawking discovered that black holes actually also emit particles. And this is a very strange result because the attraction is so strong, how can nevertheless any particle come out? But yes, Hawking made a calculation. He was surprised with his calculation himself as much as anybody else. not realizing that black holes can emit particles, but yes, they do. It is really fixed by the laws of nature, and he understood how to solve quantum field theory near the horizon, or so he thought, so particles come out. And it's still agreed today that that result is basically correct. But the details are now still very confusing and worrying, and we want to understand better how it all works. You see, by now, if you have such a description of black holes emitting and absorbing matter, you can say, well, that makes a black hole like any other ordinary physical object. Think of a bucket of water. You have a bucket of water, you can drop water out, you can fill extra water in it, and the bucket of water reacts on how much water is in it. A black hole is just like that. It reacts upon what you throw in, and then things will come out depending on how you hold it, and so on. Same thing for a black hole. So far, so good. It seems like we are doing real physics. We're making progress. We start to understand things. Now let's continue along these lines. And then came several important disappointments. We wanted to compute exactly how a black hole behaves, not only what particles come out, but also how they come out and how their behavior depends on particles going in and so on. And then we discover that there's important information in our present understanding that is simply missing. We do not properly understand how to continue. Now, I'm going to make a number of big jumps, and every now and then it will sound a bit difficult, but here the picture on the left is how an astronomer would look at the black hole. I would think of Schwarzschild himself. He says there's equal timelines. So if the radius r goes horizontally and time t goes vertically, then t is constant on these horizontal lines. And if you throw something in, you might think it goes faster and faster and will be absorbed by the black hole. In fact, it will not go faster and faster. It will go slower and slower. The reason for that is that this is here a horizon. This is where r equals 2gm. At this horizon, things slow down because all clocks there slow down. And in fact, the coefficient in front of the dt squared was how fast does a clock go near the horizon. The clock goes slower and slower and is slowed down so much that any infalling object never gets through the horizon. Similar things can be said about Hawking particles coming out of a black hole. Those particles come out at t equals minus infinity. They first come out very, very slowly, then increase exponentially, and finally they come out like this. So this would be the picture, but in this picture there's a very prominent presence of this horizon here, the dividing line between the blue and the white regions of this configuration. Think of the white region as a physically accessible region. The blue region is physically, well, you can get there, but you can't really go out. Or even if you look carefully, you see it's hard to get into the blue region because you'll be slowed down to stand still right on the horizon. So what you do when you're a mathematician is you choose a new set of coordinates where the equal timelines all convene into the same point here. Then this is the location of the horizon. And it sounds very strange to do such a thing, but if you do that, you discover that in terms of these new coordinates, where the new coordinates are again rectangular coordinates representing this diagram, in these new coordinates, the singularity disappeared. So nothing spectacular happens at all at the horizons, but the horizons now show that through nature, they're actually light fronts. In the past, there's a light front receding into the black hole, and here are light fronts advancing from the black hole, and the ingoing particles just go straight in like this. This green particle is an ingoing particle, the red dotted particle is an outgoing particle, and they just go basically along straight lines and practically with the speed of light, the local speed of light. But when you do such a thing, you realize that since there's no singularity here, I can take Einstein's equations and solve them a bit further on. So now I can make an analytic continuation of this space and time to see that there's a vast region inside the black hole, so to speak, where you can come, but you can never get out, or if you go out, you can never have come there, because these coordinates are such that its local speed of light is 45 degrees. since nobody can go faster than the speed of light, you can never go from the white region to the dark region here. And but this is then a mathematically more complete picture of space and time near a black hole. And the important information is that space and time remain regular in that black hole. But this is a slightly better diagram representing the same space and time, but now I've made a slight change at infinity. I've made a redefinition of these two tilted coordinates, the x coordinate and the y coordinate here, which are tilted, such that infinity also is represented in this diagram. This is the infinite future, and this is the infinite past at all times. And then you find that also here there's an extended region, analytically continued from the other side, which also has an infinite domain here. And then this becomes a diagram. The singularity, not the singularity that Schwarzschild was worried about, but the r equals 0 is another singularity, and that singularity now sits right here. It's the wavy line. That is a real physical singularity, not just a coordinate artifact. So this diagram is called the Penrose diagram. Penrose had the idea of writing coordinates in such a way that the speed of light always goes 45 degrees, as indicated in this little cone here. And everywhere the cone is oriented the same way. So this immediately tells you that you can't go faster than the local speed of light. So any geodesic, any path of a particle, must go steeper than 45 degrees because it goes slower than the speed of light. This also indicates directly that you can never go from 1 to 2 unless you go faster than the local speed of light. You'll have to go outside your light cone before you can go from 1 to 2 or back. So it might seem to be unnecessary to extend this metric to the other side, but then the new theory says, no, you have to do it anyway, and I'll try to explain why that is so, although the explanations actually are not so easy. Here you see the diagram again, but now I've made some changes, and the changes could be considered necessary, and many of my colleagues do say, no, this here at the top left, this diagram labeled A, is not the right diagram because I forgot something. The infinite past is not here at this wiggly line, but the infinite past is at the horizon, which was describing where particles come from in the infinite past. So this green line, that already is the infinite past, and this comes before the infinite past. But in the infinite past of a black hole, there was no black hole. A black hole can be formed by collapsing matter. Such black holes start out from a completely regular region of space and time, but then suddenly things contract and they make a black hole. We can find the solutions of Einstein's equation to that. So this is not just a hypothesis. This is real physics, real mathematics to solve the equations when you have collapsing matter. The green line here represents now collapsing matter with the letter M. And then people like Hawking, even before they found that the black hole radiates, said that this is the correct Penrose diagram, not this one, but this one. Then you can say, well, wait a minute, Hawking himself realized that there's still something missing in his diagram. A black hole also emits particles. And after it emits all energy it has, the black hole disappears. And you can calculate that again. And then Hawking said, but then in that case, this is the correct diagram. But I'm always suspicious that people run to conclusions too quickly. So I said, wait a minute, the whole theory underlying this is invariant under time reflection. So I can go from time to minus time. I should get the same diagram. But if I time reflect this diagram, I get this diagram. So I was just being naughty and saying, no, this is wrong, this is right, because the theory is invariant under time reflection. So question, which of all these diagrams is now correct? They're all different. One is perhaps more correct than the other, but which is it? Well, my claim is, in a sense, this is the only one which will survive eventually our understanding of the physical laws. These are making no sense, and I'll try to explain to you why these diagrams are to be thrown away. I'll say it very briefly now. They're thrown away because the Hawking effect that makes particles evaporate are obeying quantum equations. And also the relation between the ingoing matter and the space-time surviving much later is described by quantum equations. These quantum equations make that these pictures themselves are not correct. The only thing that would be correct would be quantum superpositions of this metric. But then you get into a very dangerous corner of our theoretical understanding. How do you quantize space and time themselves and quantize them in such a big way as would be needed in this theory? So the claim is that it's going to be wrong. We have to do something better. So how do you do this some way better? That is now the question. Here again I have a black hole. Now again the more artificial original drawing with the horizontal equal timeline, that if you want to set up a complete theory, you first have to look at a limited advance of time. What happens during a short time interval? And now the answer there is that you can answer much more precisely. This is a time interval where the total duration here is about as long as it takes a light ray to go from some distance of the black hole into the black hole. That is a short amount of time. During that short amount of time, you can calculate using classical physics, standard physics, what happens. So particles go in, but they don't get in very far. Particles run out, but they don't run out very far. And in this greenish region, I can calculate everything I want. What you then have to do next is to glue these green regions together and say, if I know what happens during a short time interval, I can calculate what happens at long time intervals by just putting these intervals after each other and go stepwise, like on a staircase. I'll go through the entire diagram. What do I get then? The answer is not as simple as it might look, because you discover that going from one slice to the next slice, you have to do some work. It doesn't go automatically. And the reason is that some particles get so close to the black hole that you didn't think of including those particles in the earlier pictures. So in the earlier pictures, some particles are missing that you get when you advance later in time, whereas some particles that went in here become practically invisible now, so you'll be tempted to lose them out of sight. Then you make a mistake. So we want to now cure the theory from that point of view. So here's my diagram again, but now I'm going to look at the time span. And now you might understand why I'm using this diagram again. I'm only using short time intervals. I'm not interested what happens if you directly cross this line without taking into account the original impact parameters, or implosion parameters, because those implosion parameters are not well enough defined. So I'm going to do the mathematical translation to the other region, but physically there are still a lot of things going on that need to be understood. To explain to you a little bit, if you let time go on for a while, you find that at later times the ingoing particles are seen to be ingoing long ago. That means they squeeze against this past event horizon. The outgoing particles, which will come out much later, at earlier times they will seem to be squeezed along the future event horizon. Squeezing the orbits of particles into such a narrow domain really means enhancing their momentum and their energies. So I have very energetic particles going along this horizon, and I have very energetic particles going along this horizon. Ignoring those particles would be a mistake. So now I'm going to say in this theory how to add those particles. And to do that right, you need to understand a little bit more about gravitational interactions between one particle and another particle. This is a very basic mathematical exercise, but a very interesting one. And the answer to that is found by first looking at very light particles, with particles of low mass, going very slowly. What is their gravitational effect on each other? That gravitational effect is extremely weak. So it's very hard to notice any gravitational force at all. But if you give these particles very high energies and the observing particle, you give it a very high energy in the other direction, then the impact energy, the center of mass energy of the collision becomes much, much bigger. And with these very big energies, the masses will grow and eventually the gravitational force will become significant. That is a calculation that you can do using ordinary standard physics. You can make a mistake, but actually the answer is straightforward. And what you find is a very peculiar thing. You find that an outgoing this green particle will be dragged along a little bit by the red one, and the drag distance, called delta U minus is the minus coordinate here, is proportional to the momentum of this red particle times a logarithmic function of the transverse separation. If this log weren't there, you would have said, okay, I'm just going to glue these particles together and net effect will be that the whole effect disappears. Now it can't disappear the effect because it depends logarithmically on the transverse parameter. So only at one value of x minus x prime, you can tune the effect to be vanishing, but then at other values, it will not vanish. So this is a very non-trivial effect that we need to take into account. Now, how do we include that? And the answer to that is we apply ordinary quantum field theory as we know it to one of these diamonds, but we have to go to the other diamonds, from this diagram to that diagram as well, and we have to combine them both in order to understand what's going on. And the reason is that if the ingoing particle is going to be squeezing against the past event horizon, its energy becomes so big that the outgoing particles are being shifted. So they don't go out as indicated here, but the arrows are broken up and they shift, as if I would cut these diagrams along the blue lines here, and then I glue them together, but shifted. So what an ingoing particle does to the outgoing particles, it shifts them about. In fact, the shift is finite, and in particular, close to the center point here, the shift gets along to the other side. Now, this will be the reason that I can no longer ignore these other parts of the diagram, because if the shift gets very big, I'll go way into the other region, which I thought was forbidden, but no, this is a way in which particles can actually transcend the speed of light and actually start to play a role in the entire diagram, not just one half of it. This is now just still a hypothesis, but then we can use that hypothesis to see what happens and then later justify this is the way it works. Now, why I'm saying it works because I'm having some preconceived notion of what a black hole should be like. A black hole should be an object that reflects whatever you do for things going into the object. It should react in such a way that the reaction is meaningful, can be described by equations which you can solve and which make perfectly sense. For instance, in these equations, probabilities must be conserved, which means I want to have, if I want to use quantum mechanics, I would want to arrive at a unitary evolution operator. Unitarity is a very important demand of my theory, and a posteriori I will check whenever I get some expressions, is this expression unitary? If yes, then I've done it right. And this is going to be an aid, a way to make sure that I'm not making any mistakes. The way to do that is to control whether your theory is really a unitary theory or not. Now, region 2 represents just the same universe as region 1. Now, what do I mean by that? We must interpret both regions 1 and 2 as representing half of our universe. Half because the total universe is just one universe. If I have them both represent the universe, I'm violating a very important concept in quantum physics, which is no cloning theorem. This region here seems to be a clone of our universe here. Many people don't look at it like this. They think this is another black hole. But then you get into difficulties. Then you say, I'm not describing one black hole, I'm describing two black holes. Physically, it makes no sense to me. So mathematically, they do all sorts of fantastic calculations, but physically, I'm saying I'm at a loss. I don't want to describe two black holes. I want to describe a single black hole. How do I do that? The answer is mathematically remarkably simple. All you have to do is find an isometry, a mapping from here to here. And if this mapping is such that the square of the mapping brings you back to the original point again, then it is what mathematically we call a Z2 group, the group which just has two elements, the interchange elements 1 and 2, and the identity element where 1 stays 1 and 2 stays 2. That is a mapping, But that mapping would generate a singularity at the origin. I don't want my physical equation to have singularities, because then I get divergences in the theory, which I will not be able to handle. But you can avoid a singularity by saying that this mapping from 1 to 2 is the antipodal mapping. That is to say, the angles theta and phi are going to be mapped onto pi minus theta, phi plus pi, and this effect are the antipodes of these theta and phi. R and t remain the same, except t is switching sign, because you see that if time runs forward here, it runs backwards here. So the time for a local observer seems to be such that the time variable here is the opposite of the time variable here. And that is very worrying, so I draw a diagram again, but now I'm drawing also Cauchy surfaces. This red surface is a Cauchy surface, the green surface is another Cauchy surface. And physics, already in quantum field theory, we often do that. We write down the particles sitting on the Cauchy surface, and then we expand the Cauchy surface to the future, and so we can solve the equations about what happens in the future if you know the present or if you know the past. But here, in this case, the Cauchy surfaces won't just move from past to future like this, but they will pivot around this point here, because what is a time translation for a distant observer turns out to be a Lorentz transformation for the local observer. And you know about Lorentz transformations, they do this with the equal time planes. And so after Lorentz transformation, the equal time plane, which is like this here, now is like this here. So simultaneity in time is being changed by a Lorentz transformation. This is a typical thing of Lorentz transformations. And that's what we have here, but again, now without doing the Shapiro shift. So doing the Shapiro shift, you need, again, to cut open these lines, and then say whenever a particle squeezes there, I'm going to rearrange the outgoing particles. So instead of cutting, I can say, wait a minute, I can be more clever than cutting. I can just rearrange the outgoing particles. And that means that any ingoing particle will sooner or later have an effect on the outgoing particles by shifting them. And this is extremely interesting. I'll come back to that for one moment later, what that does. I can say perhaps right now that the momentum of the ingoing particle is going to be reflected on the positions of the outgoing particles. And the remarkable thing about that is that momentum and position are quantum mechanically dual to each other. The particle in momentum space is the Fourier transform of particle in position space. So the ingoing particles are going to be Fourier reflected to become Fourier transformed to become the outgoing particles. And this is beautiful. This is a very powerful starting point for a theory, because until now, people thought that the ingoing particles just disappear and become unrecognizable to the outside world. Now I'm saying, no, they don't become unrecognizable. They're going to be Fourier transformed, and then they'll be seen by the outside world as Fourier transforms. This theory works beautifully, but I went a bit too fast. I forgot something, and that is that time here runs backwards. But time running backwards means that if you have a particle running here, the observer, the local observer, will see the particle run in the forward time direction. But the distant observer at the other side, after the antipodal identification, will say this is time moving backwards. So what you want is to have a particle move backwards in time. At the same time, you want to have the quantum wave functions to spread from the entire region over the entire Cauchy surface. But I don't want energy to go to minus energy, because that's not allowed in quantum field theory. So in quantum field theory, you say, wait a minute, all particles have positive energies. If I would replace time by minus time, I would get a particle with negative energy. But negative energy particles don't exist. And this is an indication that I'm going to be in deep trouble in this theory. So how do we handle this situation? I'm going to handle the situation just like Paul Dirac did when he first tried to solve the equations for the relativistic electron. He got a beautiful equation, the Dirac equation for the electron, except that the equation had negative energy solutions. And Dirac said, oh, I know what to do with that. I'll just fill all those levels up, and I'll leave some holes, and they are now the new particles. Well, that's exactly what I'm going to do here. I'm going to fill this whole region up with particles and leave some holes. Those holes will have positive energy for the outside observers. And so the outside observer will see particles that are seen as holes for the local observer here. And now the theory seems to work, and now things are coming together. So this is not the vacuum state I'm putting here. I'm putting here what I call the anti-vacuum. But that is only part of the solution, because now the particles have energies which are positive only if I say that there's a shift of the total band of the energy from minus to plus. So I'm going to shift all the particles to a constant positive, constant fixed value E maximal. That's the maximum energy you can have. And then I subtract the energy of the particles in region 1. So a particle in region 2 has the energy E max minus the particle in the energy of the particle in region 1. This way, I'm following up Dirac's own procedure. But now, E max itself represents a state which I like to call the anti-vacuum, the extreme opposite of the vacuum, the completely filled state of particles. That state I'll put here. Here, the particles going to the right are from the anti-vacuum. The particles going from the left are from the vacuum. So here you get an interesting mix between these things. And this way we should be able to make a mapping from quantum field theory in this area here to quantum field theory as experienced by outside observers. This is a new kind of mapping that still requires a lot of study. For instance, if I have the standard model here, I'll have great difficulties in understanding what kind of standard model distant observers will see near the black hole. But that's basically how we should build up the complete theory. I'm now approaching the summary of the theory. I'll explain that this theory is more or less like a package deal. I've listed some 8 observations which are essential for the theory to work. But many people never heard of some of these requirements. And when they try to make a theory, they fail. The theory generates firewalls, which are infinitely congested distribution of particles near the horizon. Those firewalls are then divergent and they make the whole black hole explode. Well, I'm going to tell you what to do with the firewalls. I have to replace the incoming particles by the outgoing Fourier particles. So, but let me list these things briefly, step by step. If you take everything together, you'll find the new theory of the black holes. So the first statement is, if you want to understand physically what to do, if you want to get the correct prescription, ask first what happens on a short lapse of time. Don't immediately include the so-called page time, which many of the people do in string theory. They talk about the entire lifetime of the black hole. But then you get gigantic problems with entanglement that you don't need at all, because just like the hydrogen atom, you first solve the Schrödinger equation for a short amount of time, and then you glue the solutions together. But gluing the solutions together is a more subtle procedure than it usually is. Because I'm only using short time shots, I can just as well take the eternal black hole as a background. At first sight, it may seem that the other regions of the universe don't contribute at all, but because of the Shapiro effect, they are going to be equally important as the other parts. So I need a isometry called Z2, a transformation whose square is equal to the identity, to divide space-time by half. This is to avoid quantum cloning, and this is to make our universe describe a single universe now for the outside observer instead of 2 universes with 2 black holes. So that I have to do in order to avoid quantum cloning. Then I have to take into account the very important notion that time runs backwards in this region 2, which I had. So to do that, I have to replace particles by holes and the vacuum state by the anti-vacuum state. The anti-vacuum state sounds like something crazy and idiotic because there seems to be no upper limit at all into how many particles you can put in the vacuum. But in the case of the black hole here, the horizon is very narrow, so the amount of particles there that fit there is also very limited. If you combine things together, you find that the anti-vacuum is a meaningful concept, and you can build up a theory along these lines, which turns out to work quite well. So that's what you have to do. And then you have to take into account the so-called Shapiro shift. So an ingoing particle is, as time goes on, you'll see that particle gaining more and more momentum along the past event horizon, so much momentum that it starts to affect the outgoing particles. So the momentum of the ingoing particles are going to determine the positions of the outgoing particles. And that means that the particle is being replaced by the Fourier transform, because position is a Fourier transform of momentum in quantum mechanics. So if you put two and two together, you find that the mapping between in particles and out particles is just a Fourier transformation at the origin. So, and that idea just works beautifully. The Fourier transformation as an operator is a unitary operator. I don't know whether you've got that from your math courses, but if you go from the basis of positions elements to the momentum basis, you find that a transformation called Fourier transformation is a unitary transformation. So I obeyed my very important condition that my theory ought to generate a unitary evolution operator. The initial imploding matter and a final evaporating matter, of course, have a very important effect on the horizons. They happened long ago, either in the past, or they only happen in a very distant future. So the effect they have on the horizon is huge. In fact, they rearrange the entire horizon. And that is the rearrangement that corresponds to my gluing metrics together in a very twisted way. That twist becomes divergent when you consider the entire implosion event, or all the particles which are evaporated by the black hole in a very distant future. Then you have to look at not just displacing the particles, but rearranging them completely. And that way you can also include the implosion and the final evaporation of the black hole in the description. It is a lot harder to do that right, so I haven't studied all the details of that yet, but it seems to be in principle a straightforward procedure as well. And finally, you have to do this not for the particles, so I've been lying all the time to you and talk about particles. What I should do instead is use the spherical harmonics. So I expand the particles into spherical harmonical waves. That I do for the momentum of the particles, so divide momentum into harmonic waves with characterized by an L and M, and a YLM, but also do that for the positions of the particles. The positions of the particles are given by the spherical harmonics YLM as well. If you do that, you'll discover that the equations are not only linear, but they completely decouple. So the ingoing particles, the outgoing particles with different spherical modes do not mutually interact, not directly, or at least not in the simple approximations that I have been using. So that you have to include, and then the mathematics works correctly if you combine all these 8 important observations together. Then you get the beginning of a very powerful theory for black holes, where you see what you have to do at the horizon is you have to cut the horizon open with your scissors and glue them together differently. And that's how the inner outgoing particles interact. Eventually, you never need to know what happens in the region 3 and 4. Remember, I had also regions 3 and 4 in the Penrose diagrams. You don't really need those regions. And that's why shifting the particles, or having these particles shift by having them go through a cut, is the same thing as just saying that I annihilate the particles here and I create them a little bit further away again. So these are the ingredients of a theory. I haven't given you much of the equations. I could write down some of the equations, but I only do that if you ask me to. And I'll approaching the end of my talk. I hope there will be lots of questions to be asked. And I have some literature here. These are the references I can give. A recent paper contains lots of these details I've been talking about now. These are somewhat older on my homepage, but much more complete. So much more calculations are shown on this much longer set of slides, actually are, but you can read them as a paper. And this is just the opposite, very pedestrian things. I wrote a little story about the investigator just crossing the horizon, a story meant for children between 10 and 90 years old. I can go on, I can write the equations, but I think I should stop here and leave the equations for if there are more questions. So I want to thank you very much for your attention.
We thank you, Professor. And as a retribution for this wonderful talk, I'll ask everybody to turn on their microphones and cameras for a huge round of applause. Okay. Thank you once again. I'll ask you to please turn off your microphones. So we already have some questions, Professor. But before that, let me give you a panorama of the audience that you have had during your great talk. So we had around 200 people from all around Brazil and even abroad, right? From Brazil, we have people attending from all the 5 regions. Brazil is divided in 5 major regions. So the North region, where we are, where I am now at this moment. So the states of Pará and Tocantins. So it's a huge region, about half of Brazil. And then we have people from Northeast region, so in the Atlantic shore, right? People from Bahia, from Ceará, from Maranhão, Paraíba, Piauí, Rio Grande do Norte. I know these names are rather strange for you, but from the center of Brazil, so where the capital Brasília is. So we have people from Brasília, people from Goiás, Mato Grosso do Sul. We have people from the southeast of Brazil, like Espírito Santo, Minas Gerais, Rio de Janeiro, and São Paulo, and people also from the far south, far from my point of view, right, about more than 3,000 kilometers away from here. So people from Paraná and Santa Catarina. We also have people attending from abroad, like people attending from Chile, and also people attending from Tübingen in Germany, right? So obviously, the major part of the audience is composed by people, local people, so undergrad, graduate students, postdocs, teachers, professors from Pará University here in Belém, but not only in Belém, but also other cities like Ananindeua, Castanhal, Salinópolis. Not only people from physics, but also people from related areas like mathematics and geophysics. And we have, of course, also a lot of people like students, postdocs, researchers, teachers, and professors from many Brazilian institutions like universities, research institutes, research centers, and observatories scattered all around Brazil. But let us then move for the first question. So the first question, as far as I can understand, comes from a master's student from Rio de Janeiro, that is Igor Moll. Igor usually wants to make the question himself. Do you want to make the question yourself, Igor?
Oh, yes, it will be an honor. Thank you.
Please
Hello, Gerard. Some decades ago, I would ask you, how did you and Veltman miss this Lyapunov-Taylor identity? It's far more easier to prove the renormalizability.
Sorry, which identity are you talking about?
Is Lyapunov-Taylor?
No, we didn't miss it at all. In fact, no, when I wrote my thesis, I was still a student and I could make all the beginner's mistakes. So I had those identities, but I thought only on shell would be useful. So to derive unitarity of the gauge theories on shell, you only need the Slavnov-Taylor identities on shell. But I had those identities in my 1971 paper, but not off shell. So the first, when I wrote down these equations just on shell, I knew exactly how to derive them. I got 2 preprints. In those days, people didn't send mails, but sent preprints around. One from Slavnova, one from Taylor. And they both did the same thing. They both said, well, you can write these things on shell. You can derive that. But basically use the same methods as I've been using. So for me, it was just a small, well, it looked like useless, but that's not true, of course. It's much more meaningful to write those equations off shell. But you get a few more terms, and I was very afraid of any complication that I would get criticized for. For instance, if you look at Slavnov-Taylor identities, there you get a few more divergent diagrams that you also need to renormalize, to subtract. But that is more dubious what that means. Then you have to ask how does the group property survive and so on. So for renormalization, it was a little bit more complicated. So I thought, well, let's only consider the on-shell expressions. But that was just, I think, well, being naive in a way.
Okay, well, thank you very much for this historical note. I did not know that. So let's go to black holes. My question is, the antipodal identification between points belonging to the horizons within the region 2 and 3 in the coordinates employed by Kruskal for the maximal extension of the eternal Schwarzschild black holes yields a projective line at the center, while the topology of the celestial sphere is preserved everywhere else on the space-time manifold. Therefore, in the construction which you are putting forward, possess a conical singularity. Am I correct?
No, there's no conical singularity. In fact, the conical singularity would come about if you would not go to the antipodes, if you just go from r and t to r minus t, because then going from to this origin will be stable. And then if you take the Shapiro shift, you get a contradiction at this point that will generate a singularity. Particles would fall just in the crevices of the metric, and that's not allowed. So, but if you go to the antipodes, you see there is r and t. R is the radius, but r does not go to 0. Whereas the angular part of the metric just is the surface area of the sphere with radius r. Now, the sphere of radius r, this r in these physical domains never becomes smaller than 2gm. That's a finite number. So if I identify the antipodes, they never come close to each other, not in the physically relevant domain. In other words, there's no cusp singularities, but that is because I'm not doing this in Minkowski space, I'm doing this in the Schwarzschild space-time. Shapiro space-time, if you, sorry, the Kruskal-Szekeres space-time. In that space-time, this point is not where the sphere goes to 0, but the sphere goes to 2gm. So all I can say is no, there's no cusp singularity, but precisely there's only one solution of the Z2, which is no cusp singularity, which is this one.
Okay, thank you. I have other questions, but I want to give the opportunity.
Yes, Igor, let's then pass to other people. So Satish Kumar, VH from Unihill, wrote a comment. I don't know if you want to make a comment, Satish, or should I pass to the other?
I will ask a quick question. Thank you, Luis. Professor Hooft, is the purpose of your construction?
Satish, I think your microphone.
I think your microphone
is a little low.
Is a little low.
Okay, you can't hear me well?
More or less.
More or less. Can you speak loudly?
Okay. So, is the purpose of your construction is to have the unitarity evolution? That's my first question.
The answer is yes.
The answer is yes.
Okay. The second question is, you have mentioned many times that there are only a handful of few results in quantum gravity that we should take seriously, right? So one of them, I think seeing from your talk, the Hawking's result is definitely one of the ones we should take seriously. What are the other ones you think we should consider important in quantum gravity? Thank you.
I'm not sure I understand what you're hinting at. To me, for a moment, this year, in most important points for black holes are these 8 points which are listed here on the screen. But for quantum gravity itself, you need much more. The theory, for instance, is not renormalizable as such. It can be made renormalizable at the expense of having a non-positive energy. So if you allow negative energies, then gravity can be made renormalizable in a way which I think is beautiful. It's exactly as renormalizable as Young-Mills theory. But you get illegal energies, and that's why people never take such a renormalizable theory of gravity seriously. But energy plays an important role in the interpretation of quantum mechanics. And that says that there are fastest moving particles, and in these very fast moving particles have energies that you can define to be zero. And that means that now I can add a negative particle, energy particle, and say its energy is defined to be zero. Let's continue and understand what quantum mechanics is. But this point hasn't been sorted out properly. So this is just right now a wild speculation that there may be a way around these energies to renormalize gravity. But the most important part, of course, is that in gravity, we have space and time themselves are dynamical variables. The metric of space-time is. And to do that property in quantum mechanics is extremely difficult. As you probably know, string theorists have said that gravity is just a particular mode of our strings. So if the string theory is okay, and we think string theory is okay, then gravity should be okay as well. But to me, that's not the complete answer, because I still don't understand how gravity acts to generate particles such as the standard model particles, how all that fits together. So I don't yet have closed equations that tell me how standard model particles relate to gravitons, and at the same time how black holes fit in the whole picture. String theorists claim to have answers like that, but I don't understand not only their equations, but also their strategy. What is it that you have to calculate? Suppose I have an infinitely strong computer. Could I calculate the mass of the electron in terms of the Planck mass? I don't think so. But the theory doesn't even give me a hint about how to do that. So there are important things missing in our understanding of quantum gravity today. So whether this is going to be string theory or whether black holes are playing a role as important as I think they do, that remains to be seen. To my mind, black holes are just an extension of the spectrum of physical particles that will also have in quantum gravity. But this time, these particles are so heavy that they get extended and they are behaving more like objects than just point particles. All that still has to be sorted out. And I'm only happy if I understand the equations exactly at that level. And this I do not, certainly not from string theory, but also not from other approaches to quantum gravity. There's a number of approaches. And yes, they're not agreeing with each other. In fact, you can find hardly any pair of physicists who is exactly agreeing about how to deal with quantum gravity. There's still lots of problems to be solved. But that also holds for the theory I've presented here. Lots of difficulties still have to be sorted out. I'm not sure whether I have.
Okay. So thank you, Satish, for your question. Thank you, Professor Toft, for your answer. So the next question comes from the state of São Paulo, the city of Campinas, Giorgio Torrieri. Do you want to make the question yourself, Giorgio?
I will make a question myself. Thanks. I have a technical question and sort of a general point underlining it, which I think reflects Igor's earlier question on text. The technical point is this diagram that you that you drew with these reflection symmetries, I mean, maybe it's a misleading analogy, but it reminds me quite a lot of a time crystal. I mean, you are shifting space-time in order to preserve rotations in 45 degrees angles in these Kruskal coordinates. And now we know there's lots of no-go theorems about time crystals as possible states, as possible coherent quantum states, or even sort of states coupled to thermal baths. My general point, I mean, I was just curious if this analogy is misleading or not. But a more general point is that there is a time asymmetry. There is a time asymmetry because a black hole forms and it evaporates, and in global coordinate systems, the past and the future look, to me, a good analogy is a high-energy nuclear collision, where you have two nuclei before, and you have approximately thermal correlations afterwards, after many, many such interactions. I do not see why you need to have a sort of globally unitary theory of how that could help.
Your first question was about no-go theorems. I'm very suspicious against any no-go theorem. If someone shows that something cannot be done, what they really mean is it cannot be done their way. And they forgot those last two words, it cannot be done. I think Bell's theorem is an example. You cannot write down hidden variables for quantum mechanics, not in the way that Bell anticipated. And there are many examples of such things that when people prove that something cannot be done, that's just, for me, that's always an indication that you should try anyway. But drop some of the natural assumptions that were in those no-go theorems. Your next, oh yes, and then you said something about time capsules. I'm not sure what you mean by that, but time in principle is a continuous variable. It's the one variable which you cannot really discretize. But what you can do is you can limit yourself to integer time steps and ask, how does nature behave after such time steps? And so we can discretize time as an artifact, just as a man-made artifact, to simplify matters and saying that at time intervals shorter than a certain basic time interval, nothing of any interest happens. Therefore, I can just go directly from time t0 to t0 plus delta t plus 2 delta t and so on. So I can discretize time, but you can do that artificially. It doesn't have to be a thing by nature. In fact, in nature, in some sense, time must be continuous, just to show how things evolve. But in our models, we can then subsequently just discretize time just like that and assume that the model makes sense. But then some models will say, well, you can better divide times in somewhat smaller units because perhaps something happens in a smaller unit of time. But that can be done added as an afterthought. In general, the discretization of time is rather artificial, I would say. But then you had some other questions which you had another. What was your
yeah, just as a sort of general principle, as you said, general relativity is unique because it's time dynamics, which is sort of part of the dynamics. But in a quantum theory, time is, you calculate a correlation function and then you measure it, and then correlation becomes, and then one of these results with a probability given by quantum mechanics is given out. Given this, I'm not sure that the eternal black hole built explicitly around time symmetries is sort of a physical thing, because initially you have a black hole forming, afterwards you have a black hole evaporating with thermal correlations, probability to find momentum correlations between particles and whatnot, which in a fully quantum theory you would get. This is a very time asymmetric situation.
Well, if you do thermodynamics, of course, you're building in some asymmetry in statistical boundary conditions, and then you have time asymmetry. But if you divide things into small enough pieces and you set up a complete Hilbert space of all possible states, then the equations become time reversal invariant. you know very well that the basic Schrödinger equation, as well as Newton's equations, as well as Einstein's equations, you can all replace time and minus time, you get the same equations back. So I don't quite see your difficulty. Of course, if you do thermodynamics, you add to that complexity. You say, now I have a very complex combination of billions of different states, and I count them differently when I start and then when I end up. So then you build in some distinction between past and future in the information part of the theory. But if you say, no, I'm going to look at sufficiently tiny regions of space-time, sufficiently tiny intervals of time, and sufficiently tiny regions of space, then the equations become entirely symmetric on a time reversal. In principle, I'm not that eager to have time reversal invariance all the way in all my theories. If eventually some asymmetry in time shows up, I wouldn't be bothered by that too much. But as yet, I haven't seen a good reason for deviating from time reversal symmetry. I just leave it like that. And in the case of black holes, the implosion effect is not that different from the final evaporation. So it's only the way you deal with statistics, it's different. And the implosion always starts with a given initial state, which then evolves to a black hole. The final evaporation of the black hole is a black hole evaporating into all possible states. So now you're doing your statistics differently. And that gives you only an apparent difference between the time reverse process and the process itself. Because people speculate about white holes. For me, white holes is just a time reverse of a black hole. It's the same thing.
Okay.
Okay, thanks.
Thank you. Thank you, Giorgio, for your question. Thank you, Professor, for your answers. And let's now move to the next question. If I got it correctly, it comes from Ronald Shellard from Brazilian Center for Physics Research in Rio de Janeiro. So, Ronald, do you want to take the question?
Okay, yeah. I cannot resist making an initial comment. I don't know if Professor Hooft remembers. A long time ago, he came to a symposium in Brazil, and we were joined by John Ellis and went to the beach of Ipanema together. And this was somewhere in February. And obviously, we went to see with all respect, the girl of Ipanema. But at the end of the day, all the girls were passing by just because they were striking. John and Professor Hooft have came from deep winter in Europe. So it was so white that it was striking. So all the girls of Ipanema was watching by. But, sorry for making a joke out of that. But my question, being a mentalist, if you have an environment on the surface of the black hole with, inducing antiparticles, if I understood correctly, couldn't you, that will induce lots of collisions and evidently emission of new particles. And couldn't you, to prove this, couldn't you calculate the spectrum of gamma rays in particular, which could be eventually observable on near the horizon of the black hole? Does it make sense, my question?
Yes, there is the theory is still very far away from such questions. But what I have here is an equation which you can read as a scattering matrix, in the sense that you have outgoing wave functions and ingoing wave functions. The outgoing wave functions are related to the ingoing wave functions by a Fourier transform in the right coordinates. So you first have to define exactly which space and time coordinates you use, then you Fourier transform. But if you take the energy of the state, so you take the in and outgoing states as eigenstates of the energy operator, kappa, then energy turns out to be conserved. The outgoing waves have the same energy as ingoing waves, and this is a result from the expansion in partial waves. So this is a partial wave with wave quantum numbers L and M. The M doesn't enter into the expression, but the L does. And this is Newton's constant. And these absolute functions you can calculate, and it's fairly, well, this doesn't mean much to you, I guess, but this is what you get if you do the Fourier transformation in these new coordinates. And this whole thing can easily be shown to be unitary. So, but these are not photons. These are just generic particles of energy which are only characterized by their position and their momentum, but nothing else. So a photon also has spin, and that's not in the rules here. So I don't know how to handle particles with spin. So this is assuming that they're only scalar particles, or at least at the distance very close to the horizon, where not the standard model, but a very, very high energy version of the standard model holds, where only point-like particles may survive and particles with spin become insignificant. But you could also say, I just left out the photons because I don't know how to handle them correctly. So eventually you have to use photons as well. But the amazing thing about Hawking's derivation is that it just used thermodynamics. And his statistics comes out to be the statistics of thermodynamics. So particles come out in a thermal state, which is slightly affected by the antipolar identification, which I wrote down here, but not very much. So it looks as if these particles are entirely thermal. They have a given temperature. That temperature is a precisely defined function of the mass. It's inversely proportional to the mass of the black hole, with just some constants in there, the Newton's constant and not much else. So, so it's just a thermal calculation, and there are very tiny corrections. Some string theorists think that there are rather big corrections, but I take it that as soon as the black hole is bigger than a few lengths, this term here will just dominate and tell you that everything comes out thermally. And then you only have to say, well, if the black hole is big enough to contain the ordinary spectrum of standard model particles, and those will come out with a temperature. And that you could measure in principle, but not in practice. And the reason is that that temperature for any astronomical black hole would be extremely small. For instance, take a black hole as light as planet Earth. Now, astronomers will tell you there are no such black holes, because the only black holes you can make by having matter collapse, like in a big star, there are several solar masses in mass, and not Earth masses. An Earth mass black hole would be just a centimeter or so in diameter. And the Hawking particles there would have a temperature corresponding to a Wien wavelength, which is a Shapiro, no, sorry, a Rayleigh wavelength, which would be the inverse, the size of the black hole. So that's a very, very low temperature if the dominant radiation has this wavelength. That's maybe millikelvin or something like that. So even the Earth would radiate only somewhere in the millikelvin domain. And that is such tiny, such weak radiation, it would never be observable unless you send an observer very, very close to the Earth and you screen the Earth from the microwave background, which is 2.7 Kelvin, which is much higher already. So, so it's going to be very, very hard to make any experimental observation, if not impossible, to make any experimental observation of Hawking particles. Even if you would be able to make that observation, you wouldn't learn much. You would probably just see that Hawking was right, and that's about it. So it would be a very expensive experiment without very detailed results.
So they are not relativistic, I mean, the particles. This is...
Oh, yes, they're relativistic. Photons are always relativistic.
No, I mean the particles, the whatever, protons, electrons.
Well, electrons will, depends on temperature. If the temperature is much bigger than the compton, then the mass in natural units, then the electrons will come out relativistic.
Okay, thank you.
So it's just thermodynamics of relativistic particles, which is, well, you can do that in a fusion reactor if you want. We know how to do it.
Okay, thank you, Ronald, for your question. Thank you, Professor Toft, for your answer. So the next question comes now from the center of Brazil, the capital. So Marcos Maia, Professor Marcos Maia, would you like to turn on your microphone, Marcos?
Yes, thank you. Can you hear me?
Yes.
Okay. Professor Toft, thank you very much for a very nice seminar. And I think that you have just created another universe for us. I have just one remark and one question. They are closely related. The remark concerns before you can use these Penrose embedding diagrams, it's necessary to define geometry at the quantum level. And this is not too clear to me. If geometry, when I say geometry, I'm talking about the Euclid axioms and the definition of parallel lines and so on. And it seems that it's not so clear that those things, the parallel lines, remain true at the quantum level.
Your hesitation, say, to accept this way of looking at things is justified for very tiny black holes. If they're so tiny that the quantum effects will become dominant over anything else. And then also you want the quantum effects of space and time. Now I'm saying what I'm doing here is a black hole which is maybe thousands of times heavier than the Planck mass. So its size also thousands of times bigger than the Planck length. At that time, the metric itself would basically be a constant. So this picture will be accurate up to 1 part in 1,000 or so, that this is the metric that you can see. And what you then do is you split gravity into a background part and an interaction part. We often do that in ordinary quantum field theory as well. We separate the fields into a background field which I keep static or simple or well under control. And then on top of that, I consider all the fluctuations. And I do the quantum mechanics of the fluctuations. And this is a well-known procedure called the background field method in quantum field theory as well. We like to do renormalization that way because renormalization comes from quantum effects and not from the background. The background is just fixed, not doing anything. Then the renormalization effects do depend on the background, and but then you have all the symmetries of the background to help you do the computations fast and efficiently. So same thing here. This metric is 1,000 times bigger, as I say, than the Planck length. Quantum effects are 1,000th of the Planck length, so to speak. So, you have a factor 1,000,000 to play around with. Okay, there's a limit to the accuracy, but the limit is something that you have under control. Eventually, we want a complete theory. So if you say, well, that's good for now, it's good for getting approximate behavior of approximate black holes. What's the real world, and how would I do the calculation with infinite precision? That I don't know. That's still way beyond me to get a theory of that kind of accuracy.
Okay, thank you. This is what I meant. I mean, it seems that we need to renormalize geometry. And this takes me to the question. The question I really have is you and Professor Veltman have proved in 1974 that Einstein's gravity cannot be renormalized. And this depends on the presence of the Newton's gravitational constant on it, specifically on the physical dimension of this constant. So it seems that you cannot renormalize gravitation in the sense of Einstein, and you cannot normalize also geometry. Is that true?
Well, I just mentioned earlier that you can renormalize gravity, but there's a price to pay. And we can't go over that without just considering what that price is and what to do about it. And the price is that you get negative energy particles. And most non-renormalizable theories can be made renormalizable by just adding garbage to it, which nobody believes to be true, like negative energy particles or negative metric particles or something like that. And same can be said for gravity. So formally, gravity can be handled to very high orders in perturbation theory, but at every order of perturbation theory, you encounter new counterterms. And we say that wasn't the rule of the game. But my answer to that is that there is no game. This is serious science. And the only rule that we accept is try to find out as accurately as possible an approximation to describe the thing you want to describe. So that we can do with gravity, and then gravity becomes sort of pseudo-renormalizable. That is to say, we can do accurate calculations, but eventually the calculations will not lead to meaningful results if you look at things as small as the Planck scale or as heavy as the Planck mass. Then today's understanding of gravity, well, string theories will tell you all, then all the other string modes will interfere in some way or other, but even that also are approximations. They start with a string which is being excited, and the string excitations can only be handled in a partial simplified way. So we still have difficulties of all sorts, and I think the ultimate answer to your question could be, and that's, I think, a very important thing that I should emphasize, that quantum mechanics is not what we think it is. If you take quantum mechanics literally as it's being taught to you at school, as you may have taught it yourself to students, then gravity is extremely hard to match with that. But there are ways to reinterpret quantum mechanics as the result of classical actions. I've been describing that in other talks. I think that's very important to say that actually at the basis of everything is degrees of freedom which behave classically. When things behave classically, you can say, oh, but now we understand what metric is. For all the classical configurations, you can write down the distance between 2 points in terms of a very complicated looking Euclidean or non-Euclidean algorithm. And you can apply all the usual theorems from geometry to that configuration. If it's classical, we understand what we are doing. And my claim is we can eventually handle quantum mechanics as well as something being classical, where we know what we are doing. But that, I didn't want to touch upon that subject too much, because then people will get angry because they have learned at school that it's not so. But eventually I think that we have to search for answers in that direction. Then we will know what quantum mechanics is, and we'll know what geometry is, and there will be no conflict anymore. But this is speculation. We haven't reached any completely useful theory that way yet.
Thank you very much. It's very nice.
Okay, thank you, Marcus, for your question, and thank you, Professor, for your answer. Let us now move to the other question. Now, questions from the YouTube, so people that are not attending from this virtual room. So the first question comes from Glauber Dorsch, that is an adjunct professor at Federal University of Minas Gerais. So he has written down in YouTube, could you use this vacuum anti-vacuum perspective to cancel out vacuum contributions to the cosmological constant? Has it been tried? Or would the anti-vacuum only make the problem worse?
To my mind, the anti-vacuum is probably not an answer to that. If you've looked what I've been doing, where is it? No. Here, in this equation, I rewrite the energy as E max minus the energy, and now so this is the opposite of that. This assumes a complete symmetry between the completely full state and the completely empty state, as if all these particles which are filling up this universe are not contributing to gravity at all. That only works if you split gravity into a perturbative part and a background part. So the background part obeys the background field equations. The perturbative part is perturbative gravity, but it has to be renormalized in such a way that this E max here somehow doesn't show up in the final equations. If I consider this as a part described in my way of doing quantum mechanics, I'm saying, of course, E max is not a physical thing. It is just a way of rearranging the notion of energy. It's a renormalization of energy, but you can renormalize energy any way you like. And this E max should not gravitate. But you should not be happy with that answer, because when I say it should not gravitate, I'm not saying it doesn't, because I don't know how to compute that properly. So the proper theory still has to be made. Then the question will be, yes, but the cosmological constant has been measured to be non-zero. That's true, but that effect is extremely tiny. It is so small, the cosmological constant that has been measured, which is not zero, is such a small number that it doesn't fit anywhere in this theory. These are tiny black holes of the size of the Planck size, whereas the cosmological constant only plays a role at sizes as big as the cosmos. So comparing the Planck size with the size of the cosmos is eventually something that has to be done. So in the ultimate theory, we do have to take into account the fact that there's an asymmetry in the cosmological constant, but the effect is so tiny that I'm not worried about such small corrections in any theory. What exactly the origin of the cosmological constant is, of course, I don't know, but I leave that open for a while. I refuse to answer the question because I don't know the answer, and I don't know how to properly think about the cosmological constant. It could even be that the observations today are due to experimental inaccuracies. That has not been ruled out completely. Some people say there's still a margin of possibilities that the observations are not what they seem to be. But even that I wouldn't care too much about. I'll just say that's as yet another domain of science to see what the effective cosmological constant is, be such a tiny number. But yes, no theory is perfect, so there will be a small imperfection in that direction.
Okay, so thank you, Glauber, for your question. Thank you, Professor Toft, for your answer. So we have many compliments. Janmai Kuma from Germany has acknowledged for the wonderful talk. Thank you very much. Bruno Ribeiro wrote that it's important to have an open mind for new ideas always. Professor George Zanelli from Chile has written, thank you very much for a most stimulating lecture. So let's now move to the next question from YouTube. It comes from Oliver Piatella. He's an adjunct professor at University of Espírito Santo in the southeast of Brazil. He has asked you, would the approach substantially change if we consider Kerr geometry?
If you consider what geometry?
Roy Kerr. Axially symmetric black hole, so rotating black hole.
Okay, yes. Well, the symmetry I'm using here is a symmetry between this region 1 and region 2, occurs also in all extended solutions of the black hole. So the Kerr geometry is rotating, but if you look at its Penrose diagram, it is exactly like this, except that it has further continuations in the vertical direction. But for my analysis, this is an unphysical domain of the theory that doesn't play a big role. So the Kerr geometry has the same two regions here, but it has more asymptotic regions which I don't think play any direct role in the physics. It's rather a role in the mathematics, in how these solutions officially continue. They make an analytic continuation. And same thing for rational neutron and also Kerr-Newman, so electric charge and angular momentum. If you combine all that, the basic domain of this diagram, these two diamonds, remains not affected. There are singularities or complications in this unphysical domain. For instance, there's even closed time-like curves there, but they don't play a direct role in this analysis. Not as far as I could see any problem with that. So, in other words, these black holes just can be handled the same way.
Okay, so thank you, Oliver, for your question. Thank you, Professor Toft, for your answer. So, Professor, we have reached 1 hour and a half. We still have some questions. Shall I go on with the questions? Is it okay for you?
Yeah, we can go on for a few minutes.
Okay, so the next question comes from Mateus Lobo from Federal University of Tocantins in the center of Brazil, but in the north region. Mateus, I believe you are in the room. Do you want to make the question yourself?
Okay, yes, thank you.
Okay.
About this cut and paste procedure, do you think it could be used in order to produce a topological hole in space-time in some specific physical situations, such as in the interior of a black hole, for instance, because as far as I understood, in your approach, it did not produce topological holes, right?
The quality of the sound was not so good, so I don't know whether I really understood the question.
Okay. Okay, to summarize, is it possible to use this cut and paste procedure to produce topological hole in space-time?
Oh, yes. In fact, this antipodal identification is an example of a topologically non-trivial use of space and time. So if I follow a path from the outside world through the origin here to this other outside world, and then say, okay, now I'm outside again, I make a rotation 180 degrees to go back, I have a Möbius strip. And it's a non-trivial Möbius strip because such Möbius strips do not occur in ordinary space-time because time is inverted. I follow the closed loop and the time coordinates goes into minus the time coordinate, much like space coordinates do in ordinary Möbius strips. So this is certainly topologically non-trivial and therefore, to my mind, extremely interesting. So you can even consider a black hole which is being formed and immediately evaporates again after that as a kind of gravitational instanton. And I speculated a little bit on that kind of instantons, but I haven't gotten very far with it because those gravitational instantons are generally not stable under scaling. Their action grows with size in general, so that means that the action is not stationary for some minimal size unless you put fluxes in. So think of an instanton with electromagnetic flux going through it, then indeed you get perhaps a Kerr black hole or whatever. And then you can say, now this instanton could be describing a quantum fluctuation that suggests that a small black hole is being formed and evaporates again immediately after. But that would be a topological instanton, a topologically non-trivial effect, which by itself it sounds very promising. We know that other topological instantons in gauge theories have produced important results. For instance, the number of family of quarks and number of families of leptons is the same. And that has been proven by the existence of chiral instantons, which would not be physically meaningful unless the number of leptonic and quarkonic generations would be identical. So there are important consequences of instantons in ordinary field theories. Maybe in the theory where quantum gravity plays a role, where black holes play a role, these instantons will also play a very important role. But I have not found out what that role is and how to get some interesting physics out of it. But I'm suspecting, and this is indeed a very important motivation for doing this research, is that we might get some more handles on how to construct standard models. Not every standard model will allow these kind of manipulations that I'm doing here. So if that is so, we might get interesting information, and we can ask experimentalists to verify whether the standard model that has arrived from the experimental observations right now, whether that model agrees with the requirement that it should also be reconcilable with black holes.
Okay, thank you.
Okay, thank you, Mateus, for your question. Thank you, Professor Toft, for your answer. So the next question comes from Manuel Malheiro from the Aeronautics Technological Institute in São Paulo State. Manuel, do you want to make the question yourself?
Yes. So first of all, thanks for this very interesting and in fact very exciting talk. But I have a question regarding neutrinos. Okay. If I understood, your symmetry is a time reverse, but is also parity. Am I right or no?
Sorry, the parity, say it again.
The symmetry you propose, t goes to minus t, still change the angles, and this change of the angles is not the change of the parity, like r goes, vector r goes to minus r, or am I wrong?
This identification from 1 to 2 is an identification where you flip the parity. So
Yes.
you will see that from the expressions that I had.
Yeah.
If you look at this, you see that t goes to minus t. Oh yes, this makes that the angular variables are parity reflected. So if you draw the surface of the Earth on a black hole, then after the antipolar identification, you would get the parity reflected map of the Earth. You wouldn't recognize it. The parity reflection of the map of the Earth is a very strange arrangement of continents that you never knew existed, but those are parity reflected. And so that's the P is -1 for this transformation. But then there's also a time reflection because time goes to minus time. So it's P times T. And then we say, yes, but what the particles themselves do is not restricted here, but I should better use a theory where the laws of physics are invariant under this transformation. And the answer is that is CPT. So I must combine the P and the T transformation with a C transformation to get a mapping under which the laws of nature are completely invariant. So that tells me what I have to do with the particles and the antiparticles. So if I go from one side of the black hole to the other side of the black hole, and I go through the center, there's also a precise prescription on how particles are changed into antiparticles.
Yes, that was my question. And in fact, I was worried if the right neutrinos could be in this part. Okay, I don't know. So it's why
the left and right neutrinos are PCT invariant, because first of all, for neutrinos you go to the antiparticles, and the P is that yes, they rotate in the other direction, but the T means that they also go in time direction. They're opposite, and PT. CP is a good symmetry for the weak force. CPT is a perfect symmetry, but if you take any combination of C, P, and T apart, is not a good symmetry of nature. That's the condition.
Okay, thank you. I thought that this right neutrinos could be seen in this minus T word, but okay.
Yes, the right neutrinos would go over into left neutrinos, but going in the opposite time direction, and therefore again. And of course, the operator C will be there as well. So you get the CP transformation for the neutrinos. Anyways, neutrinos, as we know, obey the CPT theorem.
Yes.
Whether they're left or right rotating. I must make sure that I want to have the same physical laws on both sides of the Penrose diagram.
I understand. Yes. Okay. Thank you very much. Thank you very much.
So thank you, Manuel, for your question. Thank you, Professor Hooft, for your answer. So, well, Professor, we have gone further in time, but I must tell you that we still have around 100 people, if we count together from this room and the YouTube. So let's then, if you allow us, move to the last question. Okay, so Igor, would you like to make your second question to close this session, please?
Yes, and it's an honor to close a talk with Gerard. So let me try to do my best. Gerard, the picture here proposed is based upon the eternal Schwarzschild black hole. Nonetheless, ignoring speculations regarding primordial black holes, physical black holes are formed by matter gravitational collapse. Things, using the language from Kruskal-Ezekeres, there are no regions 2 and 3 that by identification of points between those regions becomes meaningless for black holes like those from Oppenheimer-Snyder collapse.
In these regions, well, they are particularly there in the case of eternal black holes. This is the diagram for eternal black holes where I am not looking at the imploding particles. I'm not saying that they are not there, but I'm saying I'm not looking at them because they could be there, but then that was just a way of describing how this black hole got formed in the first place. But the description of the evolution during a sufficiently short time interval is obtained by using this diagram alone. And the existence or non-existence of primordial black holes doesn't change that, because the metric of them that you use to describe a finite period of time evolution would be the same. So I don't see any reason to worry about. In fact, I don't know whether primordial black holes exist at all. Astronomers are not sure of this. There is a vague hint that perhaps dark matter could be due to primordial black holes. You might well know the story better than I do. Some astronomers believe that there's still a possibility to attribute dark matter to black holes, primordial ones, whatever they are. But then the question that comes after that immediately is how could those black holes have been formed? What do you mean by primordial black holes? It's not so clear, all this, but it has no effect on this theory. The theory just describes black holes as a particle. Just as saying I have a theory of hydrogen atoms, which tells you exactly how to compute the energy spectrum of a hydrogen atom, regardless whether hydrogen was actually being formed in the primordial universe or not. As you know, hydrogen came about as very early in the early history of the universe. There was hydrogen, but whether it was there or not has no effect on my computation of the Bohr orbits of the hydrogen atom today, and that's what this theory is about for black holes.
I see. Maybe a counter argument is that in general relativity, the initial conditions of the Cauchy surface is necessary in the sense that the history of the formation of the black hole needs to be taken into account differently from particle physics. So in particle physics, I can think of an electron as an excitation of Dirac's electronic field, but in general relativity, the black holes, one needs to take into account the history of their formation.
Okay, of course, my talk lasted only about 45, 50 minutes, and that was not enough to go into this question. But in fact, the imploding matter has been taken into account, but that was so long ago that the particles that made the imploding matter had such high momentum that the outgoing particles generated by them are way shifted to infinity. They're shifted to infinity very far away. And shifting to infinity just means they left the black hole long ago. So the imploding particles generated matter that is outgoing from the black hole, but that matter has left us ages ago and is not taken into account. As soon as you say, I'm not interested in matter which was coming out of the black hole long ago, I'm also not interested in matter which will enter into the black hole in the distant future, because right now those particles are very far away. I know they're there, they're doing whatever they do in the outside universe. I don't care about them because they are not part of the system that I want to study right now. And so this effect is the Shapiro Shift, which I wrote down in here, changes everything. It now says particles which came in a million years ago have been shifted completely away because this momentum exponentially explodes. So this shift effect exponentially explodes, which means these particles have gone. They are no longer near the black hole at all. So let's forget them. And that's the answer to this discussion about including the imploding matter. Same thing for the distant explosion. The distant exploding particles are accumulating at the other horizon in exactly the same way that they have left us long ago, and the effect that caused them to explode depends on things that went into the black hole ages very far in the future still. So send in one neutrino into a black hole in the future, and the decay mode after a few days or weeks will be completely different from what it was before. So the decay doesn't depend on what the black hole is now. the black hole, how the black hole is now, does not depend on what happened at the original implosion, because these are too far away in time.
I see. Thank you very much for the answer.
Okay, thank you. Thank
Goodbye.
you, Igor. Thank you, Professor Toft. So there's another master student, this time from São Paulo, the Institute for Theoretical Physics in São Paulo. You have already touched upon it, but maybe you would like to say some additional words on it. To him is Gabriel Vidal. Gabriel Vidal, as I said, is a master student from the IFT in São Paulo, where we have the South American ICTP also in the same place. So this anti-vacuum energy suffers from the same problems as the Dirac's idea. If so, rather than holes, why can't we map just those negative energy particles to anti-particles moving backwards in time, moving backwards with respect to the already backwards time, hence moving forwards, right? So would you like to say some additional things about that, and even some final words to this Brazilian audience so that we can come to a closure, Professor?
Yes, the question about negative energies and negative time direction, what does it mean? If you, I think one has to be a physicist and ask questions. What does it mean when I see a particle moving backwards in time? You don't see such a particle. You'll see an antiparticle going forward in time. That's what you see when you write down the equations. You write down a geodesic of a particle moving backwards in time. And that's the same geodesic as a particle, as an antiparticle moving forward in time. And you know how to describe that. There's nothing special about it. So we should use the same philosophy here, the same relation between negative energy particles moving backwards in time and positive energy particles moving forward in time. Basically, that is sort of the same thing. So I don't quite see what else I can say about that.
Okay.
So maybe just then, as for your last demand, I was very happy to be allowed to give this talk, that you give me this opportunity. I hope I have been sending some message that could be useful. I can advise you to read the papers. I've sent several papers to the archives about this subject. And of course, others have quite different opinions. So it's not at all that this is the theory. This is my theory of a black hole. This is my approach. If you don't like it, well, you try something else and see which is best. I have great memories of several visits to Brazil, particularly my first visit in Rio. That was very exciting, and I still remember this school that we were visiting at that time, and the very flamboyant way of life that people were having. About it was a month before Carnival, and they were already preparing for Carnival. That was just great. And I've later returned to Brazil several times, to Sao Paulo, to Natal, but not to the Amazonia area. So I keep that. Maybe one day I'll try to visit you also. So, but for now, thank you for inviting me to give this talk.
Yes, Professor. It's going to be a great pleasure if you can come to visit us in the future. But so before closure, let me, well, I should remind that in one of your visits to Brazil, I was a graduate student at the Federal Institute for Theoretical Physics in São Paulo. So I have great memories also to having meeting you with my previous students and now colleagues in Marcel Grossman in Rome. So it has been a great pleasure. And I thank you very much, Professor, for giving us this opportunity, and hope to meet you personally in the near future. So before we close, let me ask everybody to turn on their microphones and cameras again for a final round of applause in retribution for this wonderful occasion. Thank you very much.
Thank you.